Okay, couple of points here. A line is defined by a point and a direction and a vector. By direction vector, we mean that a vector that has the same direction as the line. Well, a plane is defined differently. A plane is defined by a point. And a normal. It's a normal vector, but I'm gonna write one time a normal vector, and then from this point on, I'll just drop the vectors and write normal. And a normal vector is a vector that is orthogonal to the plane. So orthogonal. So there are forms. Let's see. There'll be a vector form of a plane. There'll be a scalar equation, and there'll be a linear equation, which is almost the same as a scalar equation. So we start with a vector equation of a plane. Okay. So suppose we start with 2 points, a known point p sub 0 with coordinate is a given point on the plane. P, a general point P, x, y, z is an arbitrary point on the same plane. And r sub 0 and r sub 1 and r are the corresponding position vector. So the vector r sub 0 and the vector r so this will set it up. Then here comes the then. Actually, let's put the point here. Then we're going to say that the vector that goes from p sub 0 to p, similar to the image that we had before, will be the difference r minus r sub 0. Okay? This is what we did before with the line. So you have a plane and you have 2 points on the plane, and if you connect the 2 points using the position vectors, that the vector that sits on the segment between the 2 points, then that will be the difference of the position vectors. And now we're going to say that the normal, or the normal, we give it a name, we call it n, for obvious reason, is orthogonal so to the plane, so is perpendicular to any vector on the plane. And what property allows us to examine whether vectors are perpendicular to each other? The dot product. Okay? So we're going to say that n is perpendicular to the vector p sub 0 p, which is r minus r sub 0, like so, right? And therefore, their dot product equals 0. So we're going to set up now the following. You're going to say that n dot the vector p sub 0 p equals 0, or n dot, since p sub 0 p is r minus r sub 0, like so, then we have this one. So this is one vector form of a vector equation, okay? Or we can split it and can say that the vector equation of the plane, of a plane, is given by, and we'll write two forms. We can have this one form of dot product, or we can clear the parentheses and say n dot r going to equals to n dot r sub 0. Either form is the vector equation of a plane. Let me, before I give you an example, let me continue a little bit here and continue to develop the other form of equation of a plane. Are you guys turning it into a discussion group over there? All right. So let's make a supposition here. Okay. Let's say we have a normal with the direction component A, B, and C, like so. And we have that R says the random direction or component X, Y, Z. And finally, R sub 0 have the specific component X sub 0, Y sub 0, Z sub 0. Okay. So we're going to write, okay, then we have the scalar equation of the plane in the following manner. So the scalar equation, remember what we had before, we have n dot r equals to n dot r sub 0. So we just substitute everything. So n dot r, we have a, b, c vector, dot r is x, y, z, and that will be on the left side. On the right side, we'll have the same a, b, c vector, dot, this time x sub 0, y sub 0, and z sub 0. I think I'm done with the split. I can bring it back for full screen, like so. Okay. So let's do the dot product. So we have on the left we have ax plus by plus cz. On the right we'll have ax sub 0 plus by sub 0 plus c z sub 0. Some people call it x naught, y naught, z naught. Or we can set it up as the following. We can combine like terms. So we'll have the direction number A multiplied by x minus x sub 0, the direction plus the direction number B times y minus y sub 0, and C times z minus z sub 0. All of it equals 0. This, folks, is the scalar equation of the plane. Okay, that's it. Now, we can also have a linear equation of a plane. Okay. We also have the linear equation of the plane, of a plane. with little effort, we're going to take this component on the right side. Notice that the right side, before we box it, those are all numbers. A, B, C are numbers, as well as X naught, Y naught, Z naught. They're all scalars. So the dot product is just a number. So we can group it together and call it negative D. So we have the following equation. AX plus BY plus CZ. And since we want to put it in a standard form is an equation where all the components on one side and 0 on the other side, we're going to add a D equals 0. So what is D? Well, D will be the right side of this equation moved to the left. So we're going to write where D equals negative the dot product. So it will be negative AX sub 0 plus BY sub 0 plus C Z sub 0. Okay? Good. So this was the introduction, and what we are ready to do now is practice, run some examples.